So remember, we finished with that question, why is the data not normally distributed, right? We went there, we collected data, why is not normally distributed? Just remember, you guys, you have to stop the video, do the test, you have to be able to do the descriptive statistics and the histograms in Excel, okay? And also Minitab after I put that other video. So why that happened? Why wasn't it normal? So you can see the data. We have minutes and shift, we have part type, and we have processing time. We took all the processing time and then put all together in a histogram. It didn't work, right? Why is that? What could be happening? Tick, 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 tick. Could be happening a few different things, right? And we have two things that may be impacting on that processing time. One thing is the part time, right? Maybe these parts, A, B, and C, have different times. And that's why our distribution is all screwed up, like the ones that we saw in our histogram. So maybe part A, part B, part C has different processing times. That's one thing. Another thing is that minutes in shift. So minutes in shift also can impact the processing time. And maybe that's what's happening, right? Depending when I collect the data, right? So I can kind of infer these two things that can't, well, I can propose these two things that can be happening, and I can test it and take a look to see how things are going to look like if I isolate the variables in that way, okay? Okay, so we did that. We did a histogram for A, we did a histogram for B, we did a histogram for C. So you can notice that I didn't change the bins so you can compare them, right? And I told you there's another way that Excel does that automatically, doing the number of bins and doing the histogram. That's why I don't like to do that, because then I don't have the power to create the bins, and I like power, right? So what do you think? Does that look like these parts have the same processing time or not? Shout the answer very, very loud. No! You can see that part-time A have a distribution that, does that look normal? It does, right? Does this normalish or something like that, right? Around 53, so pretty concentrated here. You have B that is not that normal, but you know it's a lot more spread out. So remember our skewness and choroidesis. So the different choroidesis here, right? A little bit more fat than this one. You can see a little bit more spread out. And you have C here that seems to be more about 60 something, so higher processing time, very thin, see here, right? A little bit skewed to the left and very thin, right? So with kind of a, also it could be a normal distribution, right? So because we separated into part times, now it makes sense, right? Now we have three distributions and they're kind of all looking a lot better than before. So to answer the question, does it look like part type affect processing time, right? So here we have another example of X and Y variable, right? What is our Y variable here? Well, Y variable is processing time. What is our X variable? X variable is part type, right? Part, impact, and processing time, right? So have one variable, impact another variable. Part type, is that continuous or attribute? Attribute, right? Part type is a classification. Part can be A, B, or C, right? Going back to the data, it was A, B, C, B, C, A, B, C. Processing time, is that a continuous or an attribute data? Continuous, right? Because it's seconds, right? So that have to be continuous. And here we have the summary by part type, okay? And again, I'm gonna put the Minitabs videos separate, but this is how you do the summary of processing time per part type, right? So you have the variable still processing time, but I have to add another variable there so he can divide it into part time. So you can see the Anderson-Darling test was higher than 0.05. What does that mean? Tick tock, tick tock, tick tock. Anderson-Darling test higher than 0.05 means that is normally distributed. If it's less than 0.05, not normally distributed. Okay, so it looks like a normally distributed. The shape is cool here, very as we expect it to be. We have the confidence level of the mean here. We have standard deviation, variance, skewness, kurtosis, and all that good stuff. Same thing for process B. We have it here. Now the p-value was 0.049, so it is bare there on the kind of border of being normal or not. Remember, have to be less than 0.05. It's not normally distributed on the Anderson-Darling test. I'm putting them together. Arlington, and Darling. And then, so it is technically not normally distributed, but for practical reasons, we're going to take a look at that as well. But it's really there in the border. So in a classroom examples and exams, just say that it's not normally distributed. If you find this in practice, you probably say, okay, let's move on. Let's not waste some time here. Let's consider it to be normally distributed, just because it's really on the borderline. Okay. And finally, we have process C, part type C here, which again higher. The p-value was higher, so it is normally distributed. You can see here the negative skewness, positive kurtosis here as we would expect.